Today we're going to review some theorems that we're going to use in proofs. Some of them are circle theorems, and then we will review a couple of the theorems that we've used at the beginning of the year for triangle proofs. So the first one is the fact that radii in a circle are congruent. This is handy when we have a circle with lots of radii in there. We know that they are all the same length, and it doesn't matter where they are in the circle. If you start in the center and end at the circle, they are all the same. So if I have A, B, C, and D, I know that OA, the measure of OA, is equal to the measure of OB, OC, and OD. Okay, the second theorem is the fact that congruent arcs have congruent central angles, and you have to be careful. The central angle means it starts in the center. We usually label our circle with the center value, so this is circle O, and these angles are all coming from the center. So if I say that arc AB and CD are congruent, so I can say arc AB is congruent to arc CD. That means that angle AOB has to be congruent to angle COD. There's no other way to do it. Congruent arcs have congruent central angles. So inscribed angles, we have a theorem that says inscribed angles intercepting the same arc are going to be congruent. Here's what we know about inscribed angles. If I have a single inscribed angle, and let's say this is X, and this is, I don't know, Y, then we know that Y is going to be twice X, or X is going to be 1/2 the value of that Y. So if they both intersect the same arc, which is this over here, they both have that same half value. If this is Y, then this has to be 1/2 X, and this has to be 1/2 X because they are intercepting the same arc. So if I want to number these, if I want to label these things A, B, C, and D, I can say because they both intercept arc AD, I can say that angle ABD is congruent to angle ACD. And you can kind of look at that. The angles are inscribed, and they have the same beginning and end point. They start at A, they end at D. They start at A, they end at D. So the location of this vertex is really arbitrary. As long as it's somewhere on this circle, they're going to have the same measure. So the next one is a diameter that is perpendicular to a chord, also bisects the chord and its arc. Perpendicular is the key phrase, and diameter. It has to go through the center of the circle, and it has to be perpendicular to the chord. Then everything is symmetrical, everything is split in half. So if I have A, B, C, and D, there's all sorts of symmetries in here. So it bisects the chord and it bisects the arc. Let's put the center there. So AC acts as a perpendicular bisector. We can say that BE is congruent to DE. We can say that arc BA is congruent to arc DA. And we can say that arc BC is congruent to arc DC. Everything is split in half. Now we're going to talk about just a couple of the old theorems from the first of the year, because we're going to combine these with the circle theorems and work on some proofs in class. And one that we use quite often is the fact that if parallel lines are cut by a transversal, then alternate interior angles are congruent. When you use that as a reason in a proof, you have to write that entire thing out. If parallel lines are cut by a transversal, then alternate interior angles are congruent. Here's what that looks like. If I draw a transversal, and the symbol here, the little arrows on the lines, that indicates that they are parallel. So I can say, if I want to write a statement, I can say line M is parallel to line L. And alternate interior angles would be angle 1 and 2. So we could say that angle 1 is congruent to angle 2 for that reason up there. If parallel lines are cut by a transversal, then alternate interior angles are congruent. Now there are other angles that are congruent in here. There are alternate exterior. We don't use them quite as often. And then there are corresponding. So the angle down here would correspond with the angle right here. Or 1 would correspond with the angle on top. The reasons are the same. If parallel lines are cut by a transversal, then corresponding angles are congruent, or alternate exterior angles are congruent. The next reason that we use quite often is the properties of perpendicular lines. We know that perpendicular lines form right angles. So perpendicular lines, the symbol would be this, and we can get other reasons after that reason. If we have two right angles and we want to get the angles congruent, we could say A and B. We could say that angle A is congruent to angle B because right angles are congruent. But we could also say that triangle A and triangle B are right triangles because each contain a right angle. So those are two separate reasons we can use when we start with perpendicular lines. We're going to be using the second one, I think, in class quite a bit because we use this when we want to use the hypotenuse leg triangle congruence. So we're going to list and review our congruence theorem, our triangle congruence theorems. There are 5 of them. 3 of the common ones are side, angle, side. Let me get a pen here. Side, angle, side. Angle, side, angle. Side, side, side. So those 3, if I drew them out, side, angle, side, would be 2 sides. And the included angle, angle, side, angle is kind of the opposite of that. It would be 2 angles. And the included side. And then side, side, side's pretty easy. It's all 3 corresponding sides. That one to that one, that one to that one, that one to that one. So those are the 3 basic ones. We have 2 more. We have angle, angle, side. Because basically if you have 2 angles congruent, you really have all 3. Angle, angle, side means 2 angles. Let me draw this. And that angle. And then a side that's not in between. That still works. Because in theory, you really have this other angle over here. If 2 of them are congruent, then all 3 of them have to be. So it's really just another version of angle, side, angle. And then finally you have hypotenuse leg. You use hypotenuse leg when you have right triangles. That's usually the case when you can get an angle and 2 sides, but the angle is not in between. So what we'd have to get is the hypotenuse and one of the legs. So we're going to use some of these in class to work on proofs with images in circles. So we combine these triangle theorems with the circle theorems.